Okay, so uh, the first the first kind of uh, the presentation is sampling theorem for band-limited random process. By band-limited, we mean uh, it's not changing radically. It's not like radical change. If it's like that, then it's not band-limited. In frequency domain, as we mentioned, it has very wide band. Band-limited meaning in frequency domain is band-limited, and in time domain it has its behavior is not changing drastically. It has a certain way of changing that makes it band limited. So a deterministic real signal with Fourier transform is called band limited if it is zero for outside of a certain band. In other words, if f is outside of a certain band, it you see that is very close to zero or zero. Okay, so then where W is the highest frequency content in Xt. Such a signal is uniquely represented by samples of Xt taken at a rate larger than 2W. In other words, if the bandwidth is W, then you take samples higher than 2W, you are actually taking full advantage of the information inside it, and it will be uh, recoverable from those samples without any loss of information. That is the famous Nyquist theorem. That is a well-known Nyquist theorem. And though we may not be talking about the details of the Nyquist, but that is a rule of thumb and also has theoretical foundation in which you like to take samples two times as a bandwidth, two times, more than two times as a bandwidth, then you get reasonable samples to represent that process. Okay, so the minimum rate Fn equal to 2W samples is called the Nyquist rate. Then for complex value signals is one half of the frequency support. That is, if W and W2 are the lowest and highest frequency components, lowest and highest frequency component, then 2W is like that. So you like, in other words, you want to take sufficient samples. And what is the sufficient sample? 2W. The answer is 2W. So that is uh, many years ago concluded by Nyquist. The signal can be perfectly reconstructed from its sample values if the sample rate is at least equal to 2W. The difference, however, is that the sample values are complex in this case, and for specifying each value, you need a complex number. Two real number. A complex number is represented by two real numbers. Okay, so this means that a real signal can be perfectly described in terms of 2W real numbers per second, or it has 2W degree of freedom, or real dimensions per second. Okay, so this is, I'm not sure if everybody is familiar with the idea of degree of freedom. When we are talking about how many samples, we need a sample because that sample has freedom to move around, right? That sample has the freedom to move around, and we call it a degree of freedom. We call it a degree of freedom. And why not 2W plus 1? Why not? Because 2W plus 1 dimension, if you make two 2W plus one dimension, that extra one dimension is going to be represented by the original 2W. The original 2W can fully represent the whole thing. So if you make one extra dimension, it's not necessary. It's just a waste of your resource. So we are saying that it has 2W degree of freedom, but not 2W plus 1, because not one extra is redundant. Okay, so to speak. So for a complex signal, the number of degree of freedom is 4W, just because of real part, imaginary part, which is equivalent to 2W complex dimension or 4W real dimension. But imaginary numbers are created artificially. The originated by our assumption about complex number. We put an extra imaginary dimension. We call it J, right? We call it J, and then two real numbers to represent one complex. One represent the real part, the other real number represents the J dimension, right? So that's it. It's artificial. So sampling below the Nyquist rate results in frequency aliasing. The band-limited signal sample and Nyquist rate can be reconstructed from its samples. Band-limited signal sample and Nyquist rate can be reconstructed from its samples by the use of interpolation formula. So, in other words, if you are representing a band-limited signal by 2W samples, you do it reasonably, it's good enough. In terms of if you want to reconstruct it, you use this formulation and you get a perfect reconstruction. You get a perfect reconstruction for every time instant. And then of course there are intervals. There are intervals. The interval is xn divided by 2w. Okay, so there are samples of xt taken at t equal to here. So it's like, let's see, you have a sample, you have a band-limited signal, you take samples. You take it with 2w samples. Now, you are saying that, you're wondering that, how about those points that are not in the sample? Are they gone? Are they gone? No, the answer is no, they are not gone. If you take samples for 2W samples, you use this equation. You actually reconstruct the whole thing, including those not sampled. And the reason is this is band limited, so they don't move that fast. They don't move very fast. They move slowly. Okay, that's the whole business about band limited. If they move too fast, then the band will be expanded. Then you need to take more samples. Okay, so they move reasonably slow, so you can reconstruct the whole thing, including samples not between your time instance that reconstructed. Okay, so and then the time instant is n divided by 2w. N divided by 2w. So then you have index for n. Equivalently, xt can be reconstructed by passing the sample signal through an ideal low-pass filter with impulse response sync to Wt. Okay. So this is a sample, right? This is a sample. and we want to reconstruct it, what we do is we multiply the sample with sinc function, with this one with sinc function, and this is like, think of it as linear combination of sinc function samples. But if you see the index more carefully, you have this index and this index for t minus, right? With respect to t minus. So this is like a convolution. So you pass that sample through impulse response sinc function. So you get a convolution, and then you get this summation outcome. So equivalently, the construction can be done by passing samples through impulse response sinc of 2WT. Then figure 2.8-1, which we see later. Note that the expansion of xt as given in this is an orthogonal expansion, but not an orthonormal expansion. Okay? It's orthogonal. This sinc is designed carefully so that they're orthogonal, but not orthonormal. Because if we do inner product of one with the other, we get this instead of one. For orthonormal it needs to be one, but not right, not the case. So we get orthonormal. A stationary stochastic process is said to be band-limited. Stationary is said to be band-limited if its power spectral density is 0 for f larger than w. Since Sxf is a Fourier transform of the autocorrelation function, it follows that Rx tau can be represented as this. Okay. So, in other words, this is band limited, and its Hall spectral density is also band limited. Well, we talk about band limited business here, so that applies to autocorrelation function also. So if Sxf is Fourier transform of autocorrelation function, then Rx can be taken samples, right? You can take samples on Rx and following the Nyquist rate. So you get this sample multiplied by sinc function Rx tau. So it's the same story. You have Rxn divided by 2W, and samples are taken at here. Now, if xt is band-limited stationary process, then xt can be represented as something like that. You have this is like another version of it. You have xt represented by this, which is similar to this. Okay, so we are looking at sampling and reconstruction among samples. You have xt, and you take discrete samples. Notice that you are taking discrete samples. So that is sample xt here, 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 here only. But because they are band limited, so as I like to emphasize, this is band limited. It changes slowly instead of something like very fast. It changes very slow. So it's very slow as long as you take samples that is sufficient enough, and then you multiply with your basis, which is the sinc function. That is the basis, and then you reconstruct it by linear combination of the basis, then you get the original signal back. Okay, so in terms of the equations where you have this interval n divided by 2w, x is taken at this t equal to this and that, and This is the sampling representation for stationary stochastic process. The samples are random variables, right? When you take samples, it's random variable. Instead of a deterministic sample, it's a random variable that are described statistically by joint probability density function. If xt is a y-sense stationary, then a random variable represents a y-sense stationary discrete time random process. For continuous process, y-sense stationary, you take discrete samples. Then the samples represent a y-sense discrete time. Emphasize this term, discrete time random process, because you take discrete samples. Then the autocorrelation of the sample random variable is given by this. You take that sample with respect to this sample and you take expectation. That's what happens here. Right? What happens here? You take expectation with respect to another sample that is a few samples away in time index. Then that is Rx of n minus m2w. And again, we apply previous formula. This Rx is integration of minus ww. It's one cycle in the frequency domain, and its power spectral density by applying inverse discrete time Fourier transform, and you get this relationship. So if the process is filtered with white Gaussian noise, no, I'm sorry, let's say that again. If the process is filtered white Gaussian noise, then it's zero mean and its power spectrum is flat. What that means is if you have white Gaussian noise, you get F, right? In F domain, you get 0 divided by 2. But you filter it with what? With a band. With a band. That band goes from minus W to W. As the outcome, you get what? You get something like this, right? It's band limited because all this power is gone, right? This power is gone because it's filtered. So that's what it means by filtered. And it's a zero mean, and this power spectrum is flat in minus W and W. In this case, the samples are uncorrelated, and since they are Gaussian, they are independent as well. So the signal representation can be easily established by showing that equal to 0. Okay. Hence, equality between the sample representation and stochastic process holds in the sense that mean square error is 0. Okay, so I think we go up to this point, and then that's it for today. Yeah. Thank you for your attention.